And so first we'll go through a warm-up, an introduction to the pigeonhole principle, some common problem-solving scenarios that you'll probably see in Math Olympiad and competitions. And then after that, we'll do some practice in the handout. So I'll give you guys around 1 minute to do both the warm-up problems. They should be pretty straightforward. You can just test them out. The first one is if you have 10 black socks and 10 white socks all mixed in a drawer, how many socks must you pull out without looking to guarantee you have a matching pair? So after pulling out some number of socks, you always have a matching pair, no matter what. And what's the minimum number of people needed in a room to guarantee that at least two people have the same birthday month? So no matter how many, like, no matter the birthday month of the people, as long as we have this number of people in a room, we always have two having the same birthday month. I'll give you guys 1 minute to try out these two problems. Oh, okay, it's been around a minute. Does anyone have any ideas on how to solve the first problem? Yeah, seems like Melody and Chris are both correct. So, Melody, can you tell me how you got three socks for the first problem?
Because the worst case scenario is you get one black sock and then one white sock. So if you want at least guaranteed that you have more matching pair, you have to have three.
Yeah, so we always look at the worst case scenario for the minimum number to guarantee, right? Because if we don't look at the worst case scenario and we take like second worst case scenario, then what if we get the worst case scenario? Then there will be like one black sock and one white sock, as you said. And Chris, how did you get 13 for question two? Uh, Chris? Yeah. So there's 12 months in a year, right? And for the worst possible case, we would have 12 people all having different months. And over here, if we have 13 people and there's only 12 months, and we use 12 people having different months, then the last person must share a month with someone because there's no 13th month. Okay. So the pigeonhole principle basically states that if we have more than n items, which are known as pigeons, and we are given n containers, which are the pigeonholes, then at least one container must contain more than one item. This is also known as the Dirichlet's theorem or the Dirichlet's principle, I'm pretty sure. Oh, and this basically just states if you have more stuff than places to put the stuff, then some place has to hold more than one thing. We can visualize this by having our containers. So, or we can just have oh crap. We can have spaces. Let's have five spaces and let's have, let's say, six balls, right? Or like seven balls. The worst case scenario is if we have one over here, one over here, one over here, one over here, one over here. Oh yeah, we go for the worst case scenario because we try to contradict the claim in the pigeonhole principle. We try to say that if we have more stuff than places to put the stuff, then all places to put the stuff holds at most one thing. It can't hold, we try to contradict the claim, which is why we have the worst possible scenario. So now we've put 5 of our balls into these 5 positions, and we still have 2 left if we have 7 balls, right? Which means one of the next balls must go over here. And now we have 1 ball left. With this last ball, can we guarantee 3 in one space? Just tell me in the chat. Yes or no? So we have 1 ball that has yet to be allocated. Oh, yeah, we can't guarantee that we get 3 in one space because this one could just go like over here. Which means, yeah, if we have 7 stuff and 5 places to put the stuff, then some place has to hold more than one thing. So we'll cover this example question. If we have 11 socks in a drawer and there are only 5 colors of socks, then prove that at least 3 socks must be the same color. So here, what are the pigeons and the pigeonholes? You can just unmute and tell me. Yeah, the pigeons are the socks and the pigeonholes are the drawers. So pigeons are basically elements or items that we try to sort, and pigeonholes are like categories or groups. And in this case, if we have 11 and 5, right? Okay, this is a sock. So we have 11 socks and 5 different categories. Does anyone know the relationship between 11 and 5? So basically 11 equals 5 plus 1. 5 times 2 plus 1. Whoops. And do you know what is special about 5 times 2 plus 1 in this scenario? It means that if we allocate 2 to each different category, then we will still be left with 1 left over, which means the 1 must go into one of these 5 categories, right? That's the worst case scenario. Or if we use pigeonhole principle, then, I think it's in a corollary, yeah. Okay, we'll go on to example 2. In a school of 367 students, prove that at least 2 were born on the same day of the year. I'll give you guys, oh no, just tell me why this works. Tell me in the chat or by unmuting. Oh, okay, no one's saying anything. Basically this, oh, what?
What?
Oh, okay.
Uh,
Yeah, so there's only the number of pigeonholes that we have, which is the number of categories of birthdays, exact birthdays, is at most 366, right? And so we have n containers, n equals 366, and the number of items, pigeons. So the pigeons are the students, which is 367. So now by pigeonhole principle, we have more items or pigeons than containers or pigeonholes, right? Because 367 is larger than 366. And then we can just say, because the number of pigeons is greater than the number of pigeonholes, by pigeonhole principle, we must have at least 2 students born on the same day of the year. So do you know why in this case 366 may not work? It's because this is a school with multiple year groups. So there might be a year where there's 266 days and someone might have a birthday on February 29th. And how many students do we need for three people to share a birthday? It's basically just going back to this problem where we have 11 socks in the drawer and only five colors. But now it's like a much larger number with 366 different categories. Just tell me the expression, like some number times another number plus one or something. Yeah, so it's 366 times 2 plus 1 because we can just take worst case scenario. What about four students having the same birthday? Aiden, it's not quite 366 times 4 plus 1. Think about it. If we have three students sharing a birthday, it's 3 minus 1, which is 2, times 366, and then plus 1. So for 4, we have to do 4 minus 1, which is 3, times 366, and then plus 1. Yeah. So now what do we do about n? If we want n students, some number of n, having the same birthday, how many students do we need to have? What's the least number of students to guarantee this? Yeah, it's 366 times n minus 1 plus 1. So this is a corollary of the pigeonhole principle. Given that kn plus 1 pigeons are given that we have kn plus 1 pigeons and n pigeonholes, one pigeonhole must have strictly more than k pigeons, right? So that's basically what was going on in this example about the what about n example. What about the n case? So this means that one pigeonhole must have at least k plus 1 pigeons. I'll give you guys 2 minutes to try to prove this. And try not to say we take the worst case scenario. Okay, it's been around 2 minutes. So does anyone have any idea on how to prove this? You can unmute or tell me in the chat. So we want to rigorously prove this without saying we take the worst case scenario, because that's not really a proper proof. So can someone tell me in the chat what method we use to prove this? Yeah, melody, that's the correct like pathway. So do you know what the method is called? Uh, so the method is called contradiction. We try to prove, so we basically just assume that this is not true, and then we try to show that if this is not true, then math just doesn't work, kind of. Like we usually run into a 1 equals 0 case or something similar. So over here, we are given kn plus 1 pigeons and n pigeonholes. And we say, and this says that we must have one pigeonhole having more than k pigeons, which is more than or equal to k plus 1. So how do we prove this? How do we show this by contradiction? What's our contradictory statement? What do we assume to get a contradiction? We want more than k pigeons, so what should we take as like the opposite of more than k pigeons? It says one pigeonhole must have more than k pigeons. So the contradictory statement would be all pigeonholes must have less than or equal to k pigeons. So we must have, firstly, all pigeonholes fulfilling that they have less than or equal to k pigeons. And do you know what's wrong about this statement? Oh, wait. So for notation, we usually say for the sake of contradiction. We usually, wait, how do I move this? Okay. We usually say something along the lines of, for the sake of contradiction, to show the marker that we don't actually think this is true. And we also shows the marker that what we're trying to use to prove this. So for the sake of contradiction, we have to assume, assume that all pigeonholes have less than or equal to k pigeons. And why does this cause a problem? Can someone tell me in the chat why this assumption does not hold? Be brave. You can unmute and tell me as well. I think that's easier. Aiden, do you know why we run into a problem when all pigeonholes have less than or equal to k pigeons? Okay, no reply. So basically, at the start of this, we were given that we have k. Oh, because sometimes there's only one in each. This is with kn plus 1 and n. So we don't really count that case. It would be more correct to just say that there's k in each. So we're given that there's kn plus 1 pigeons at the start of the problem. So we know that our contradiction has to lead to something to do with kn plus 1, right? Because if we have, like, say, less than or equal to if we are given, let's say, kn pigeons, then we can just have k pigeons in every single pigeonhole, which results in all pigeonholes having less than k plus 1 pigeons, right? So that doesn't guarantee one pigeonhole having at least one pigeonhole having more than k pigeons, which means kn plus 1 is a special number in this case. So we need to relate our assumption back to kn plus 1. And our assumption states that all pigeonholes must have less than or equal to k pigeons, right? So now we can take the worst case scenario without saying worst case scenario in the proof by studying the inequality. So we assume, we can create an inequality. This shows that number of pigeons, I'll just call it hashtag P for number of pigeons, is less than or equal to K, right? Because we have less than or equal to K pigeons per pigeonhole. And how many pigeonholes do we have? We have N pigeonholes, right? So the number of pigeons is less than or equal to K times N. Or this is just equal to Kn, right? Now, does anyone see like a contradiction? A contradiction is when there's two statements that can't be true at the same time. So math doesn't really math anymore. Just tell me in the chat. I'll give you guys a hint. You can also unmute to tell me. So basically, our contradictory assumption states that if we have less than or equal to k pigeons per pigeonhole, then we have a total of the total number of pigeons will be less than or equal to kn. But we are given kn plus 1 pigeons at the beginning, right? Which already doesn't make sense because if the total number of pigeons is less than or equal to is less than or equal to kn, and we have kn plus 1, then this means that kn plus 1 is less than or equal to kn. And can this ever be true? We have a number plus 1 is less than or equal to itself. If we rearrange this, we get kn cancels. Oh, I missed. And then we can move this 1 to the other side, or we can just keep it here. And we get 1 is less than or equal to 0. Does this work? 1 is less than or equal to 0. It doesn't work, right? 1 can never be less than or equal to 0. So we have a contradiction. This is a sign for a contradiction. I drew it pretty badly. I'll just search it out for you. Contradiction symbol. Uh, there's multiple ways to write it. Okay, I'll just write it the way that Google writes it. So this is a way you can write it, and then this is also a way that you can write it, I think. Yeah. So our contradictory assumption, where we suppose the opposite of this claim is true, cannot hold, which means this claim must hold. So this tells us that given kn plus 1 pigeons and n pigeonholes, one pigeonhole must have more than k pigeons. This seems like a pretty straightforward statement, right? Because we just tested it out with this example. But actually, it seems like it's pretty hard to prove, right? So how many students must a school have to guarantee matching first and last initials? I'll give you guys 30 seconds to try this. Yeah, Melody, that's correct. So over here, we have first and last initials. Let's call that X and Y. So now we're no longer just considering one number, we're considering two, right? We're considering a pair. We're counting the number of pairs. So X is the first initial, Y is the last initial. How many values of X can we have? How many different X's can we have? We can have 26, right? Because that's the number of letters in the alphabet. What about Y? It's also 26. So how many pairs of X and Y can we have? Right? Because now our pigeonhole is the pair of initials because we're trying to guarantee a pair of initials as the same. So that's our pigeonhole. Yeah, so it's 26 times 26, which is 676. And we want to use pigeonhole principle to guarantee that we have uh, at least one pigeonhole with more than one pigeons. So going back to our pigeonhole statement, we just need more than n, more than the number of pigeonholes. We just need the pigeons to be more than the number of pigeonholes. So we need a number of students, hashtag S, to be greater than 676, or in whole numbers, this is the same thing as being greater than or equal to, wait, not necessarily, but in this case it is 677. So the school must have at least 677 students to guarantee matching first and last initials for at least one pair of students. The next problem is that there's 23 students in Miss Jones's class. Each student must be assigned to one of five groups, and what's the minimum number of students who must be in the same group? So we have 23 and 5. Wait, did I do the wrong number? Oh, must be minimum guaranteed. Whoops. Oh, I'll just type it out. Okay, I worded this problem really badly. So minimum guaranteed. Number of students who must be in the same group. Because we could just have one student in one group, or we could just have 0 students in one group. So just try to use what we just proved, kn plus 1 pigeons and n pigeonholes. So over here we have 23 and we have 5. Yeah, Melody, I worded the problem wrong. Oh, I think it's supposed to be maximum as well. The answer is not 19 if we want it to be guaranteed, right? Because guaranteed means we have to consider the worst possible scenario as well.
But you can't have a group of 0 people, right?
Yeah, but we have to be able to guarantee the same group. We don't get to choose the groups, just saying. Yeah, the answer is 5 because 23 is 5 times 4 plus 3, which means we have 3 left over. Oh, 5 times 4 plus 3. And this 3 left over, as we discussed earlier, like at the start, if we have more than 1 left over, it doesn't really change anything as long as it's like less than the number of categories. So over here we have 3 left over, which is the same, which gives us the same result as having 1 left over, which means that we will have at least 1 pigeonhole with at least 5 pigeons. Okay, now we'll move on to some common scenarios that you'll see in problems. Uh, this is a pretty common scenario where we're required to construct intervals to solve it. We have 10 people have heights between 150 and 200 centimeters. Prove that there are at least 2 people whose weights. Oh, I typed it wrong. Whose heights differ by less than 6 centimeters. Um, I think I already gave you guys a big hint to solve this problem. We have to construct intervals. I'll give you guys 30 seconds to try it out. And just tell me in the chat if you think you have the solution. Okay, first of all, was this problem statement kind of intuitive? Did you see the problem and immediately think, oh, this must be true? Or was this problem not as intuitive and you had to like solve it first? Hmm. Oh, it was intuitive? That's good. So basically, we have 10 people and heights differing by less than 6 centimeters that we want to prove. So immediately, we should probably think of what if we have heights differing by at least 6 centimeters? Oh, wait. Yeah. So we want to basically just have the opposite of this problem statement whenever we have these word proof problems. So if we do that, we have a range of 60 centimeters, right? Oh, wait, no, it will be 6 times 9, which is 59 centimeters. So we have a range of 59 centimeters, right? Oh, wait, no, 54, sorry. 6 times 9 is 54. We have a range of 54 centimeters, right? And over here we have a range of 50 centimeters. So that should be pretty intuitive. So how should we construct our pigeonholes? We want to construct how many categories to get 10 people to take up more than the number of categories. Okay, let me reword that. So we have 10 pigeons, 10 people, and we want to choose the number of pigeonholes that we use, right? And we know that pigeonhole principle only works if we have more pigeons than pigeonholes, right? So how many pigeonholes should we just like use? What's the safe amount? No, we can't use 10, right? Because that would mean we have the same number of people as pigeonholes. And that just means we can have one person per pigeonhole. Yeah, Aiden, we need 9 pigeonholes. We can have 9 pigeonholes to be safe because that means we have 10 is greater than 9, and 10 is the smallest whole number that's strictly greater than 9, right? Which means it's basically like a safe pigeonhole principle thing. So if we choose 9 pigeonholes, how should we construct the pigeonholes? I gave you guys a hint in the slide. We construct intervals, right? So what should the range of each interval be? Yeah, Aiden, 6 centimeters apart. Yeah, but does it have to be exactly 6 centimeters per interval? Can someone tell me in the chat, does it have to be exactly 6 centimeters per interval? Or can it be different values? It doesn't have to be exactly 6 centimeters, right? Because we just need 6 categories and each category can be something different. So we might be able to have one category being 5 centimeters, one being 7. Oh wait, no, one being 5, one being 5.5, and then one being and the rest being 5.9 or something. That probably works. We just need less than 6 centimeters, less than or equal to 6. So to be extra safe, let's say we use 6 for all of them except for the last one. This gives us these ranges. It's easier to type them out, I think. So we have 150 through to 156, right? Oh, so this square bracket means a closed interval, which means we include 150 in this interval, and this round bracket, circle bracket, means an open interval, so we don't include 156. So in this interval, it basically says we go from exactly 150, including 150, all the way up to a number that's infinitely close to 156, but it's not 156 yet. So we take this interval, we can take this interval, we can take this one, and then dot dot dot. And then after that we have 198 and 200. So does anyone know why I used closed intervals, closed and open, for each of these intervals, except for the last one? Just tell me yes or no in the chat. I don't know if they'll mark it down in NZM mode for this, but this is probably important to just have an idea of. So the reason why we use closed and open for these is so that these categories don't overlap, right? So if we have these categories overlap, then that just kind of makes Pigeonhole go a bit funky, and then it just doesn't really work as well as we want it to. And the last one can have both as closed because it's like the last one, there's no more 200 and 206, right? And also it's only 2 as well because we used a difference of 6 per. We can do the math. 198 equals 150 plus 48. That indeed works. So now that we've set up our 6 pigeonholes, our 6 categories or intervals, I mean our 9 categories, we have 10 pigeons, right? And we have 9 pigeonholes. What should we do? We can use pigeonhole principle, right? Which means no matter what heights these 10 people are, we must have at least one pigeonhole or one interval with 2 people having a a height within that interval. So we might have one person here, and then we have one person in each one of these in the dot, dot, dot. And then we have one person here, right? This is the worst case scenario. And then we have one person left over. So for the person left over, they must go into one of these intervals, right? Which means one of these intervals must have at least two. So say it goes into this one, then we have two people having a height from 150 to less than 156, right? Which means their heights will differ by less than 6 centimeters. Does this make sense? Okay, that's good. So given 10 points on a 9-meter ruler, prove that there are 2 points no further apart than 1 meter of each other. It's basically just the same as the other one. We just construct 1 meter intervals. So now this is a pretty, I think, counterintuitive one. So given a set of n positive integers, there exists a non-empty subset whose sum is divisible by n. Do you guys have any ideas on how we can prove this? So basically, a set is like a collection of n positive integers. It might be like 1, 2. If n is 5, we can have 1, 2, 3, 4, 7. Like any n different positive integers. Oh wait, no, any n positive integers works. And then a subset is like a selection from the collection. So a subset of 1, 2, 3, 4, 7 can be 1, 2, 3. It can be 1. It can be 4, 7. It can be 7. And it also can just be nothing. Wait, no, in this case, it has to be something. So our construction to solve this seemingly daunting problem is that we take the n integers to be a1, a2, all the way to an, right? And then we take these basically consecutive sums. So over here, if we set this to be our set, then we have a1, a2, a3, a4, a5, or an. And then we take the sums s1 equals a1 equals 1, s2 equals a1 plus a2 equals 3. And then we keep going, s3, s4, and s5. So what's special about us taking these consecutive sums? Can someone tell me in the chat why this is, oh wait, why this is a pretty smart way to do this? What might we do? What's the next operation that we're going to do to S1, S2, S3, S4, S5 that makes it so that using these consecutive sums, it's easier? Uh, it's not triangular numbers. Think what happens if we do S5 minus S4. So let's just think about it. If we have, let's say, a different type of sum, if we have n 1 equals A1 plus A2, and we have N2 equals A1 plus A3 or something. Why would this not be very suitable for this type of problem? What's the difference between S2 and S1 and N2 and N1 that makes S2 and S1 a better choice for this type of problem? What happens if we do S2 minus S1? We're left with A2, right? What happens when we do N2 minus N1? We're left with A3 minus A2. So we have a minus sign. That's not very convenient because we have a plus sign and a minus sign in the same expression with positive integers, whereas in this one, we just have pluses. So if we do S5 minus S1, we get A2 plus A3 plus A4 plus A5. And then it's basically all just consecutive sums, and we know that they always sum together to something. That's basically why we use this type of consecutive sum or subsequent sum. I'll just finish these. So the next step, oh, wait. So the next step is setting our pigeonholes, right? Because now we have our, we don't have our pigeons yet, but we set our pigeonholes. Can anyone tell me what we set the pigeonholes as? We want some sum from A1, from some sum from AI to AJ. It can be any I, and then after that to J. Oh, I set A5 to be 7 to just show that any like set of numbers works. Set of positive numbers. So we can set our pigeonholes to be remainders modulo n, right? Or like remainders when you divide by n. But then that gives us 0, 1, dot, 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 n minus 1. Now, how many pigeons are in here? I mean, how many pigeonholes are there in this list if we count each one of these as pigeonholes? From 0 to 1 to 2 to all the way to n minus 1. This gives us n pigeonholes, but then we have some number, let's say n pigeons, right? That wouldn't work. So and also if we have 0 as one of these, then we're already done. Because that means we have some difference. Oh, wait, we have some pigeonhole that we hope to construct, giving us 0. And remember, our pigeonholes are like some AI plus AJ plus AK, something like that. Like, and then you can keep going if you want, or you can delete some stuff if you want. So if we have 0, we're already done, so we don't need to worry about 0. So we just care about 1 through n minus 1. So we have n minus 1 pigeons. And then what should we take as our pigeonholes? Well, something we can take as our pigeonholes is just the difference between two of these sums, right? Because that gives us some type of sum of like consecutive elements in our set. So our pigeons are going to be something like S5 minus S1, S5 minus S2. Oh no, we can just do S5. Wait, sorry, I got it mixed up. So our pigeons are just going to be the sums of S1, S2, S3, S4, S5, which gives us 5 different pigeons. And then what's n minus 1? That's because we just want to take modulo 5. We want to take 1, 2, 3, and 4 modulo 5 as our pigeonholes. Because if we have s, any of these s's being 0 modulo 5, then we just have some sum from A1 to like A3, A4, or A5, or A2, or just A1 by itself being divisible by 5. And that's not good because that like that just means it's already solved. So we just want to look at 1, 2, 3, and 4. And then these 4 different remainders modulo 5, or like remainders upon dividing by 5, are our different pigeonholes. So we have 4 pigeonholes. 4 pigeon holes. And how many pigeons do we have? We have 1, 2, 3, 4, 5. 5 pigeons. And 5 is greater than 4, so we have 2 of these sums must be in the same pigeonhole. Let's say it's Si and Sj, where I and j are some different numbers from 1 to 5. And let's say j is greater than I. We can do this because if we have I is greater than j, it will just be symmetric. So we can say without loss of generality, j is greater than I. And then we just take Sj minus Si equals A1 plus all the way to Aj minus A1 plus all the way to AI. And because we set j to be greater than I, we will have some leftover terms of AI plus 1 through to AI plus j. This is just equal to AI plus 1 plus dot 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 plus AJ. And now we have a subset, which is AI plus 1 through to AJ. So our subset will now be, oh, that's not well drawn. AI plus 1 dot dot dot, oh, AJ. So we know the sum of this thing will be divisible by n. This is pretty confusing. I suggest you just read over the slides in your spare time. So another application of the pigeonhole principle is the party problem. Given a group of n people at a party, we need to show that at least 2 people know the same amount of people. So to make this problem simpler, we just get rid of the people who know 0 people first, right? And we also know that no one can know n people, right? Because if they know n people and there's n people at the party, they know themselves. So we just assume that doesn't work. So this gives us capital N equals n minus k if we just remove the people who know 0 people, because they really shouldn't be at the party if they know 0 people, right? And this also just makes it more simpler. And now each person can know exactly 1, 2, 3, or all the way to n minus 1 people, right? When we have n people, a capital N. And given that we have capital N people and only capital N minus 1 different categories of people that we know, of the amount of people that we know, then by pigeonhole principle, we have more pigeons than pigeonholes, right? Because our pigeons are the people and our pigeonholes are the amount of people that they know at the party. So we must have 2 people being in the same pigeonhole, right? Which means they must know the same amount of people. Does this make sense? Tell me in the chat. Just say yes or no. Sort of. What are you confused about? The problem was that given small n people at a party, we need to show that at least two people know the same amount of people. So let's say all of us are at a party. I know three people, Aiden knows four people, and you know like one person or something. Yeah. Okay, so another type of pigeonhole problem that you'll encounter is geometric pigeonhole. So a pretty common one is that if we have 10 points inside an equilateral triangle, we need to prove, or with side length 1, we need to prove that there is at least one pair of points that are at most distance 1/3 apart. Uh, I'll just explain this one. So for this one, we have an equilateral triangle, and we have 10 points. 10 times dot. So if we have a problem that asks, we need to prove that there is at least one pair of stuff that fulfill a certain distance, like fulfill a maximum or minimum criteria, then we must immediately think, oh, it has something to do with pigeonhole or something. So to have 10 give us, oh, we have 10 pigeons, right? Oh. And to use pigeonhole on 10 pigeons, how many pigeons, oh, wait, no, how many pigeonholes must we have if we have 10 pigeons? What's the maximum number of pigeonholes that we can have? Yeah, we must have strictly less than the number of pigeons, right? Which is 9. Okay, so now we have at most 9 pigeonholes that we will use. And because we just want to solve the problem, we should try to use as many pigeonholes as we can, right? So to use 9 pigeonholes, how should we split up an equilateral triangle into 9 pigeonholes? We can split it up into 9 pigeonholes like this. Oh. Pretend these small triangles are all the same. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9 pigeonholes. Or like 9 small areas, right? So each small area, each small triangle has distance at most how much? If we know one entire length of this large triangle is 1, and these equilateral triangles are all the same, but they're like really badly drawn, then what's the maximum distance inside one of these equilateral triangles? Must be the side length, right? And what's the side length of these equilateral triangles? Can someone tell me in the chat? Must be 1/3, right? So we know this is 1/3, this is 1/3, this is 1/3. So all of these side lengths of these small triangles are 1/3, right? And we have 9 different small triangles. Or they're actually identically the same in dimensions, but they're different triangles in our configuration, like different areas. And we have 10 different pigeons or points with 9 different pigeonholes. or categories, which means we can just use pigeonhole principle because we have more pigeons than pigeonholes. So there must be two pigeons, at least. There must be at least one pigeonhole with at least two pigeons, right? By just applying pigeonhole principle. It might not look like that would work, but then it must work because this is pigeonhole principle. So we must have, let's say, two inside this triangle. And then we know that the distance is at most 1/3 and we are done. Are there any other stuff? So an alternate form is that if the average of n numbers is k, then there must exist at least one number that is at least k, and one number that is at most k. This is pretty easy to prove. It's not really pigeonhole, I think. You can just prove it by contradiction, like we proved the corollary of the pigeonhole principle over here. So the lesson's now finished. Try out the handout problems in your spare time. I think there's a few fun problems, like near the end. But they should be pretty easy for you guys. Does anyone have any problems? Like